Introduction. Okay, I think we can get started. Welcome to the Great Lakes Seminar Series. We have a very good participation in the room, and actually we have a number of remote participants as well, so that's great. I am Ayumi Fujisaki Manome. I am an associate research scientist at SIGRA, and it is my pleasure to introduce Dr. Claire Pettersen as today's speaker. Claire is currently an assistant professor in the Department of Climate and Space Sciences and Engineering department at the University of Michigan. She joined Michigan in 2022, so she's a relatively new faculty member there. Before joining Michigan, Claire worked as an engineer and research scientist at University of Wisconsin-Madison for more than 15 years. She was involved in a number of projects, including lake effect snow studies funded at Cooperative Institute for Meteorological Satellite Studies, or CIMS, which is another NOAA Cooperative Institute. Claire's research is focused on cold season and cold location precipitation, such as snow, mixed phase rain, as well as cloud thermodynamic and synoptic characteristics. Claire's research lies at the intersection of science and instrumentation and utilize ground-based airborne and satellite observations of cloud and precipitation. Claire has been involved in field campaigns on Greenland ice sheet and Antarctic ice sheet, which sounds great, since 2004. Then her research has been supported by NASA, NOAA, and NSF. And most notably, she was a recipient of the 2019 NASA Early Career Award, and she is currently a Mercator Fellow for the Arctic Amplification Project. With that, I will turn it over to Claire.
Thanks, Ayumi. Thanks, everybody, for being here. This is great. I've had a really nice visit with folks. I'll put my timer on. I have lots of exciting stuff to share, but I'll try to not use too much of your time. Yeah, so today I'm going to talk about something near and dear to my heart, and it happens to be in the Great Lakes region. Some of our research we've done specifically kind of oriented around Marquette, Michigan, and this is especially special because it just had its 10th birthday. So I'm going to talk about some of the studies that come out of that. But first, I wanted to give you an overview of me. I have kind of a strange or unusual career arc, as Ayumi alluded to. So I started my engineering career working in the Antarctic ice sheet, building and deploying optical modules. That's what you see here in a very young version of me in the South Pole, so South Pole Station in Antarctica. And from that point, I got recruited by Space Science Engineering Center, which is what houses CIMS, the Cooperative Institute for Meteorological Satellite Studies, to work on a climate satellite called Clario. Didn't launch, but part of it's on the ISS, so that's good. We call that a win. And this was in Madison, Wisconsin. Both IceCube and SSEC was in Madison, Wisconsin. I also got to do a lot of ground-based and airborne campaigns. This is me with the ER2. We had put the scanning HIS, which is an infrared interferometer on that. And so a lot of NASA and NOAA flight and ground campaigns I was fortunate to be part of, and eventually led me to decide I wanted to do a PhD while doing my engineering work. So I went to part-time engineer, full-time PhD student, and I was fortunate to work with the Ice Caps project. So it was really confusing going from IceCube in Antarctica to Ice Caps in Greenland. But this is a ground-based instrument campaign funded by the NSF, located atop the summit of the Greenland ice sheet. I was really fortunate to be part of that group, and I actually continue to be part of that group now. One of my grad students is working on ice caps. So I just give people that introduction, especially students or early career people, that you can have any kind of career path. There's lots of fun ways you can make your way to being a researcher or faculty. All right, today I want to talk about what my group's currently doing, and that's focusing on precipitation observations. And what I mean by that is we've done a ton of work with ground-based suites, like I mentioned. We work with observations and deploy observations in Greenland. We've done some stuff in Scandinavia, and of course we have the observations in Marquette I'm going to talk about today. We also, part of the reason we do these ground-based observations is to help inform and work with satellite science teams, of which I'm part of. So we coordinate these satellite observations or statistics from satellite observations with these ground-based sites to give us some insight into precipitation processes. Of course, we're working with all these different federal agencies to support our work. We've been fortunate to work a lot with NASA, NOAA, NSF, and the National Weather Service. So I wanted to focus on, don't worry about all the words, I just try to feature some of the work that's come out of my group. But Marquette, Michigan, we've been really fortunate to have an excellent observational database there, and it's produced a lot of really interesting work, and I'm going to focus on talking about that today. But just so you know, we work in a lot of different places. This is some highlights of our Greenland work. So for those of you interested in Greenland precipitation processes, I'm more than happy to talk about it. We've also done a lot with the Scandinavian Peninsula looking at precipitation. And finally, like I mentioned before, working with a lot of satellite obs, GOES 16, CloudSat, and GPM. And this is some of the work we have either in publication or in process. So for those of you who might be interested in some of these satellite observations, I just want to let you know I'm happy to talk about those as well. So please follow up with me. I'm more than happy to talk about any of these studies. So I'm going to focus on wintertime precipitation in general. I don't probably need to tell a bunch of people in Michigan why we should care about this, but I like to give an overview. Why does this matter? Well, wintertime precipitation, whether it be snowfall, rainfall, mixed phase, impacts our society, right? So it makes it harder to get to work. You have to plan around it. There's not just planning for you, there's planning for Department of Transportation. There's planning for industry, like, are we going to open our building today? There's planning for universities, bus systems, etc. So characterizing winter precipitation and forecasting it accurately is really important. The more we know about wintertime precipitation and how it behaves, the better we can serve these stakeholders. I love this picture. This is from Madison, Wisconsin, our Beltline. Look at that echelon as like some teamwork right there. This is after a really serious snowfall that came right at the morning rush hour, and we have this echelon of snowplows deployed by the Department of Transportation at just the right time, right, to facilitate all of that traffic behind them to get to work. And of course, this is from Marquette, Michigan, in the UP. Not only do they have snowplows up there, they have these industrial-sized snow blowers because they actually need to really move the snow further away because they run out of room up there with all the snowfall they get. So there's a lot of logistics behind, that we need to better characterize snowfall so that these people can have an easier time for planning, and so we can all be safer. It also matters on a global scale in terms of thinking about climate. We care about the world's global ice sheets. Snowfall is what builds these ice sheets, right? And importantly, not only is this about ice mass, but it's also about albedo, right? It changes the properties of the surface. Here's November 2020 to February 2021 in the Great Lakes region. It looks very different, right? And the shortwave radiation that's incoming into our atmosphere and to our surface is going to interact with the surface very differently because there's snowfall on the ground. And even rain changes that too, right? So all these properties are also important besides just the mass characteristics. Of course, this is also important for water resources. This is Sierra Nevadas, right? And so this is thinking about how much winter to winter can you change your snowpack? Highly variable, especially in places like the West Coast of the US that are experiencing swings between major drought years to what's happening right now with a major atmospheric river that flooded all of JPL. So February 22, 2019, you can see there was a really big snowpack, whereas February 19, 2020, you have minimal, right? So these big swings, understanding the characteristics of the snowfall helps us better understand and predict for water resources. And of course, forecasting. I don't need to tell probably people in this room because we've all experienced it. We have anecdotal experiences like last week on Tuesday, that Clipper system, that is a really hard thing to forecast. It comes down from Alberta, it's super narrow. It might dump 5 inches, might dump 1 inch, right? And so that's really hard to forecast. This is just an example from February 2021 of what the forecast was for Southeast Michigan. You see Ann Arbor here was predicting 8 to 12 inches. A lot of stuff can affect forecasts and forecast models. Snow microphysics, like the ice habit, the crystal shape, how much riming there is, the accretion of super cold water, snow to liquid ratio that tells you about its density, and surface. We're complicated here in the Great Lakes because we have all these cool surface impacts. We have open water. We have a lot of air surface interactions, turbulence, orography. I like joke, people are like, orography, what are you talking about? When it's really dry out, a little orography goes a long way. Okay, you don't need a lot to like create a fair amount of snow. And we actually have some cool studies out of Marquette that show that. So this was the forecast, did a pretty good job. This was what was realized with the observations. So, you know, Weather Service does a really good job nailing these down, but partly what we do is provide them observations and information that can help further hone those forecasts. Lastly, I want to say why wintertime precipitation matters, and this is something we're getting into more and more, is that precipitation phase matters. And I do a lot of work in the Arctic where we think about, and actually matters here too, what happens when you have an unusual amount of wintertime rain in a place that has permafrost, in a place that has snowpack? If you have a lot of wintertime rain here in the Great Lakes and you have snowpack, all that rain just runs off into the lakes and changes the hydrology. Doesn't go down into the soil, right? So they're seeing this in the Arctic too, extreme levels where it's eating away permafrost. This is what's being shown here in Alaska. We were lucky enough during our Scandinavian campaign to sample an atmospheric river. I don't know if you can read this, but I love this Twitter title. Raging storm in Scandinavia just now. Storm Erd and Orkan strength is angry. It was like, it actually like shut off a couple of our instruments for like 12 hours. So these are really important because rain on snow events are highly destructive and they can eat away snowpack. They can eat into permafrost. They can create a lot of hydrological impacts. So hopefully I've convinced you to care about this. You know, this depends on the crowd, but probably everybody here cares about wintertime precipitation. How do we observe snow? You think, oh, just, you know, take a ruler. It's easy. Snow is really hard to observe. This is a good example, what I'm showing here, a couple different ways to observe snow. So what you can see on the right are these two bucket gauges. They have these little flappy things. They're supposed to help with the wind. They help a little bit. They're called alter windshields. And then to the left, there's this big, huge fence system. So that's what's called a double snow fence. It's a double fence intercomparison reference standard. So in the middle of those two fences, the wide one and the narrow one is another one of these buckets. And the point of that fence is to deaden the turbulence right above the buckets. So snow will, like, instead of doing this and follow the streamlines, it will actually fall directly in. So this is not easy to deploy. You can see the amount of structure that had to be built to have this. So unfortunately, we can't just put these everywhere. This is a site at Met Norway, and in Norway that we added some additional ancillary observations. What you see here, and I'm going to talk about more, is a small profiling radar. That's that dish you see. That bright light is facing a camera recording a particle size distribution. So we're trying to get other pieces of information at strategic sites that are already measuring snowfall to try to put all this information together to try to build a picture of how the snowfall characteristics, both macrophysical and microphysical, are behaving. We, of course, need to use satellites. Like, I'm not going to say we can do everything at the ground. At the ground, you get this high temporal resolution information for one point. But we really need to know what's going on globally, right? And we don't really have a way to measure precipitation over the ocean other than satellites, right? So this is just an example of the A-train. This is now, sadly, all of these ones have departed us, but they served a good purpose. And CloudSat and of course Calypso are two that we've used for precip and clouds. I'm part of the GPM science team. We also use that for precip. But even though satellites give you global coverage, there's some limitations. First obvious limitation is you get a swath, right? You just get a swath at certain points of the day. So you're gonna have gaps. But some other limitations that people might not be aware of is any radar signal you send down from a satellite is going to have a signal from the surface that kind of is too noisy to get precipitation information from. So that's called the radar blind zone. Different surface types impact your retrievals. And of course, clouds can have impacts if you're relying on some kind of infrared information or visible to give you some information about surface snow. That's really going to be a limitation. We, of course, use spatial scanning radar from the National Weather Service. This is a great figure. This is from NOAA. And what this is showing you in the kind of tan color is the coverage for a specific scan up to 4,000 feet above the ground, and where it gets to up to 6,000 feet and where it gets to 10,000. So you can see we have gaps. The biggest place we have gaps is in the mountain west. Mountains are going to block signal. Can't do much about that. But you'll notice in the Great Lakes, even though we have good coverage, remember this is saying like where it's seen to 4,000 feet and 6,000. A lot of the snowfall and precipitation we get forced by surface interaction, like lake effect snow, is way below that. So we actually have a lot of gaps in our NextRad data network here in the Great Lakes as well. Finally, we get all this radar information we get all this information about reflectivity from radars. It's not saying you have X amount of snow. It's saying you have a X amount of return signal. Like you have this much reflectivity. From that reflectivity, we have to get actual physical properties of precip, right? So if we have our scanning radar here, it's looking at a parcel of air. Radar reflectivity roughly corresponds to diameter to the 6. I'm not going to get into that too much, but let's pretend this radar says, I see plus 15 dBz. That could mean it's seeing a bunch of small droplets in that volume. Could also mean it's seeing a couple large droplets, because the reflectivity is proportional to the distribution of particles you have in that air mass. So reflectivity is inherently ambiguous. So getting Z to R relations is difficult, right? You have to make assumptions. When you talk about snowfall, it gets even more complicated. We don't have this dBz to diameter to the power relation that's fixed. We also have a couple other things going on. If you have, again, plus 15 dBz, you could have a lot of small snow particles. Plus 15 dBz could also mean a couple big particles. That same reflectivity could also mean you have heavily rimed particles, which changed the mass a lot, but didn't change the reflectivity. You could also have all different kinds of crystal habits. We've all seen this. You walk around and you're like, ooh, that one's really sparkly. It's also sparkly to a radar. So the problem is that now getting reflectivity was already ambiguous for rain. It's ambiguous for snow, but now we have these extra factors that we have to think about in our assumptions. So hopefully I've convinced you that measuring snowfall is not easy, or rainfall for that matter. So this comes to some key questions that I'm going to talk about with the work we've been doing. So how do wintertime precipitation, macro and microphysical properties vary by surface, boundary layer processes, location, orography, and or environmental conditions? We're looking at this like regime kind of perspective. And how can we use innovative combinations of ground-based and space-borne instrumentation and leverage them to examine these precipitation properties? And then can we take all of that and categorize precipitation events by regime with distinct like environmental or location-based properties that will help illuminate key processes? And these could further help us better forecast rain and snowfall. So let's come back to our observations. And I'm going to focus on Marquette. And we've had a bunch, we've been really lucky. It's been such a great data set. We've had a bunch of papers come out. I'm going to focus on this top paper, GMC, because it gives you a nice background of the snowfall work we've done there. But then I'm going to hint at some of this more recent work we've done. And depending on time, I might have to speed through some at the end. But let's get into it. Why Marquette? Well, there's a lot of snow in Marquette. If you're going to do a field campaign, there's some key things you need to do. There's no perfect place, but like make sure you have reliable logistics, like power. You know, it sounds really basic, but you'd be surprised, especially if you work in Antarctica or Greenland. People who are willing to help you out, which the NWS has been amazing. And then you want to make sure your probability of looking at whatever process you want to look at is pretty high. So Marquette, this is old. This is 2013, 2014. They get a lot of snow there. We also have an abundance of snowfall types. And that goes back to me talking about the regime idea. We want to test if like microphysical characteristics are different when you have these broad swath different regimes. So what I mean by that? Well, fortunately, everyone here in Michigan is familiar with lake effect snow, but it's a mesoscale process. And you essentially have a cold air outbreak. So you have cold, dense air coming from Canada. It comes over the relatively warm and open lake waters. So that surface layer is quite warm. So now you have instability. It's like, nope, I don't like this. I'm going to mix it up until I make it all equilibrated. So you get this convection as you get further along this fetch. So the fetch is the traverse along the lake. You get more convection until you build up lake effect clouds. And then you get more until you make snow. And then that little bit of orography on the other side, on the lee side, that helps a little extra lift and you get a lot of snow. And you can see this. These are the Great Lakes snow belts, okay? These are defined by the preferential wind directions when you have these cold air outbreaks, okay? So everybody here is probably familiar with it. I will make a caveat that lake effect snow in Superior and Marquette, very different than the type of lake effect snow they get in Buffalo. There's quite a different classifications, but they're all due to this instability of this cold, dense air over this relatively warm surface, moist air. Here's a nice animation of some lake effect snow going across Superior. I feel like, I don't know how easy it is to hear, but you can really see these cloud streets increasing, getting kind of brighter, wider, more convective as you go across the lake here. But lake effect is not the only type of snow we get in Marquette. We also get synoptic scale or system snow. And this is, I love this figure because it points right in Ann Arbor. That's convenient. But this is a really nice figure from the Illinois State Water Survey, obviously a bit older, but showing a lot of these types of low pressure systems that traverse into the region. So Alberta Clipper, I mentioned from last week. So you see that type 1. We have a lot of storms that come up from the Gulf with all that moist air and bring it up here. In the wintertime, we have Colorado lows. So these are some preferential tracks if you were to take like a self-organizing map or something like that and break them up into different kind of common synoptic pathways. All right, so I've convinced you that we have lake effect snow. We also have system snow. We're just gonna stay with that really broad swath. So what we did in 2014, Mark Cooley had a NASA Early Career Award and was able to augment the Marquette site with some enhanced instrumentation. And so we were able to put 2 instruments there at the beginning. And this was January 2014. And these were optimized to look at snowfall. But we run them year round, so we have all kinds of precipitation information. Also, happy 10th birthday to the Marquette suite. This is like keeping a suite like this running for 10 years takes a lot of like patching stuff together. We started with the early career grant, which was awesome. And then we had GPM ground validation helping support it. And then NOAA Weather Program Office has supported it. So I'm really proud that we've been able to have 10 years because you don't have a lot of multi-year data for these kind of suites. So this is really important. I'll talk about that kind of at the end. All right, so what we first put there was a micro rain radar. It's a simple, like you can see it here on the left, it's a profiling radar. So that means it just stares straight above and it lets weather traverse past it. So you get really high information, time height information. That's what's shown here on the top. Reflectivity, which people are familiar with from weather radar. Doppler velocity, people might not be as familiar with, but it's telling us in a general scale, the air mass, how much is falling towards or away from the radar. So that's going to incorporate the motion of the particles, but also the air. Okay, so you have to do a little magic to get those apart. But you get so much information here. There are other products we get from the radar too that I'm happy to talk about, but I'm not going to talk about in this talk. One thing about this is it's just run forever. This thing, I think, has been hit by lightning once. We've had the cable run over by a snowblower. Had to buy a new cable, not cheap. But it has like 98% uptime or something like that. So we have this great data set. Originally was made to be on ships. Really, we've put these all over. We also have the precipitation imaging package, which is I'll show a little video here. So you can see in the bottom right, we have a bright halogen lamp and a camera. Pretty, at the time, a high-speed camera, but it does the job. You're seeing this big open space and you get to see in the video how snowflakes are falling through it. It then uses a bunch of image processing software to get statistics and information about the size, the fall speed, et cetera, of those particles. This was developed by NASA, by Larry Bliven, and I've worked with him for a long time as the NASA instrument mentor to keep these going as much as we can because they're such valuable observational instruments. They're really simple. It's my favorite thing is when something's really straightforward and simple and produces a lot of data, right? So from this, we get particle size distributions, fall speed distributions. We also get snow rate and effective density estimates, and I'm going to talk about that more towards the end. All right, so the goal of this work, both my 2020 paper and Mark Cooley's 2021 paper, was like, let's look at these regimes. So let's take data from multiple winter seasons in the Great Lakes region, partition using the MRR. So we're just going to do a simple partitioning method with MRR. We're going to augment with data from the PIP, the precipitation imaging package. And then we leverage coincident NextRad information from NWS, forecaster observations, and reanalysis. And then we wanted to showcase that these instruments coupled with an operational center like NWS could enhance forecasts and help our understanding of snow events. So basically, this is an example from a spatial context from NexRad, as well as a vertical context from the MRR. So NexRad at the top, MRR at the bottom. On the left, we have system or synoptic snowfall. And on the right, we have lake effect or mesoscale snowfall. So what's really neat about this is just, okay, so like people are really into machine learning now. Our brains are really good at machine learning. You look at that and be like, those patterns look different. So I've kind of handpicked these, but these are patterns that persist when we look at deep synoptic snowfall versus shallow lake effect snowfall. For example, the system snowfall is pretty uniform. Like it's both like fairly uniform reflectivity spatially and vertically. I mean, there's some variation, but it's pretty uniform, especially when you compare to the lake effect, where you can see those bubbly convective features. You can see the cloud streets. You can also in the vertical see that pulsed nature, right? As those cloud streets come through, you see that high-low reflectivity. Very different patterns, right? So now what we've done, this is spatial for one time point, and then the MR showing time height. We want to show this in a composite way. So we did these 2D histograms, and all you're seeing here is on the y-axis of both these is height, the x-axis is reflectivity, and the color scale, and I apologize, I no longer use JET. This color scale, the color scale is showing us the density of the counts. So it tells us when we see like proportionally, it's a 2D histogram. It shows us some information. So deep snow by definition is gonna be deep. That's per design. Shallow snow is anything more shallow than 3 kilometer. And what you notice is deep snow by definition had to get to 3 kilometer above the ground. But the majority of the shallow snow is almost like only 1 kilometer above the ground. That's really shallow for considering how much snow we get, which I'll talk about the accumulation in a minute. We also see some interesting features from a composite sense. Now, this is not one event. This is a bunch of events together, so we can only extrapolate so far. But in general, the deep snow, once you get below two kilometers, it's pretty invariant, like that reflectivity is not changing with height, whereas the shallow snow sees this massive growth. It has to, right? Like it's forming in such a shallow layer, we have to see a lot of growth from 1 kilometer to the surface. It just shows how productive that shallow snow is. We also coupled our deep and shallow regimes with, unfortunately, Marquette, we don't have radiosonde launches, but we use the ERA 5 temperature profiles just to look at some like, what are the environmental conditions? What are kind of the basic conditions we see during these? Deep snowfall is warmer than shallow. We expected that, but it's nice to have confirmation, right? Deep snowfall is these advecting from the south and southwest, and we're expecting warm air advection when we have these. Shallow snow is colder, and also shows a lot of temperatures in that kilometer above the ground in the dendritic growth zone, right? We just looked at the reflectivity. We know the snow is growing really fast. For those of you who are unfamiliar, the dendritic growth zone is between about -12 and -18C, and it's this area, it's this range of temperatures that optimize, snow just explodes in growth. And I'm happy to talk about that after offline. I have an extra slide, but that's something the forecasters look for when they're trying to forecast snowfall. In terms of relative humidity, unsurprisingly, the deep snowfall has higher relative humidity throughout the boundary layer into the free atmosphere, where you really see that peak of relative humidity for the shallow right at the top of the boundary layer. So I'll spend a little time on this because this is particle size distribution. People might not be as familiar with this. This is data from the PIP. Again, we're looking at a 2D histogram composite. This time it's normalized, but essentially the brighter areas are higher counts, higher percentage of counts. So the easiest way to look at this is the x-axis is diameter, okay? It's just diameter of the particles. You can think of the y-axis as a number concentration. That's not strictly what it is, but for all intents and purposes, let's just say it's number concentration. It's hard to see here, but these are actually very different, and this is composited, I forget, like I think there's 160 individual deep snow events and like 300 shallow snow events. So this is a lot of data. It's hard to see it here, but when we difference them, we see differences. So I'm subtracting the shallow snow from the deep snow. So wherever it's red is showing characteristics that are much more prominent in the deep snow, and the blue is showing characteristics much more prominent with the shallow. Again, we have our N on the y-axis, D on the X. When we have deep snow, and all of this is statistically significant out to 6 millimeter diameter. When we have deep snow, we have more small particles. We just see more small snow particles during those events. And we see a much narrower size distribution. So you're just having more small particles, fewer large particles. When we have shallow snow, the biggest thing that came out of this is we have way fewer small particles. So when it's in that dendritic growth zone, no joke about explosive growth. They're all just going from like ice, like tiny ice nucleus to like pretty big dendrites. So we have way fewer small particles, a way broader size distribution, and this has led to more large particles. We just couldn't get significance on it. That's why there's a question mark, but we're pretty convinced that there's way more large particles. We also wanted to use the PIP to say something about macrophysical snowfall qualities. So we want to say how often, like what's the occurrence of each of these types, the deep and shallow. You know, again, deep is synoptic, shallow's lake effect for the most part. And what we found as a function of month, and this is like 6 years of data, the occurrence looks like this. Way more shallow snow than deep snow. Anyone who lives in Marquette would not be surprised by that. We see an increase in shallow snow till about January. Then we see it decreases in occurrence, whereas the synoptic pretty much every month is about the same frequency, minus November, but it's pretty much the same frequency. Well, I meant to replace this with the recent one, but this is from a couple of years ago. This, of course, has to do with the coverage of the Lake Superior ice cover. If we look at this, and I apologize, it might be kind of hard to read, months are on the bottom, ice concentration on the top. We have the min and max years, and then I have 2022 because this was the last time I looked at it. Of course, this year there's virtually zero lake ice cover right now on Superior. But what if we look at this, we see on average around the end of January is when the lake on average tends to, start to fully close. So what happens to our snow, our lake effect snow, our shallow snow? Well, this is a really cool animation where we have some different satellite products together. Anywhere there's ice is being shown this cyan. So we see the lake ice here. And then here we see this nice open area. And this is such a great example. Yeah, you still get some clouds over the lake ice, but you see how different it is when you have that open water. You clearly have the cloud streets. You clearly have the convection, right? And they're right next to each other. It's just that you have that open water. More open water, we have more lake effect. So now we can explain why this is happening. And again, this is one of those studies we knew this, but it's so great to have the data to help us understand the process. Increased cold air outbreaks as you go from November to January. However, end of January, on average, not this year, on average, you have this increase in lake ice cover. So then you start to have decreased lake effect snow because you have the lake ice cover, and you start to have decreased cold air outbreaks into the late winter, spring. And so we have an explanation of this pattern. All right, so in terms of occurrence, 68% of the snow occurrence is shallow, 32% deep. When we go to accumulation, we're almost equal, 50-50, right? So now we're taking, like, we're adding up. We're doing that thing I told you was hard to do, this Z to S, right? But here we're using the PIP, which actually gets values of accumulation. So almost equal. This means that there has to be a higher snow rate and denser snow when we're thinking about the deep snow, just based on like the current statistics. The shallow snow, unsurprisingly, lower snow rates, less dense, but still impactful, right? Happens a lot. We also looked at the winds. I'll probably just zoom through this because it is pretty clear, but I have all winds in the red. This is a wind rose. So the wind rose is showing us the direction, right? North, south, east, west. And then we're seeing percentages of time we have winds out of a certain direction. So we have all winds year round, winter winds, deep snow, and shallow snow. If we look at these, unsurprisingly, the vast majority of the deep snow is coming out of the south-southwest. A lot of those, remember where I showed those synoptic systems coming from? A lot of it's there. And the shallow lake effect, mostly out of the northwest, north-northwest. This is all logical. This makes sense based on our location. But I want to talk about these. And this is something we explored in Mark Cooley's 2021 BAMS paper. These deep snow events that came over the lake. So here I have an animation that I made of the ERA5 surface mean sea level pressure. And hopefully you can see that this low pressure system is passing to the southeast of Marquette, which is in that star, right? So we see this pass. And as this moves around, you can see the winds change. So let's look at the next rad. So I made an animation of what's happening with next rad during this. okay, so that looks like our system snow. Oh, something's changing. Oh, wow. Now we've like become lake effect, right? So this goes into the same timing where you have this low pressure system coming, bringing system snow, but then as it passes by and moves around, you start getting some cold air coming over the lake and creating lake effect. So we wanted to dig into these types of events, which we call lake enhanced synoptic, and see what kind of transitions we see based on our enhanced instrumentation. So at the top here, we have MRR reflectivity, time height, reflectivity in the color. In the middle, we have the PIP particle size distribution. That's just telling us something about the number concentration as a function of diameter. The third one, we have height, and then the color bar is relative humidity. So we can see it was very high relative humidity, and the dendritic growth zone is outlined. And the last thing, we have snow rate and snow liquid ratio. All right, this is about when we see the transition at 0Z, so that's convenient. We clearly see an enhancement in the lowest kilometer in the radar, in the profiling radar. At the same time, we very clearly see a shift in what the particle size distribution looks like. It goes from relatively narrow, a lot of small particles, to fewer small particles. You can see that diminishing red, but a lot of big ones. We also see at the same time that dendritic growth zone in that moist layer went from being quite high in the atmosphere to deepening. So this deepening of the dendritic growth zone means we have more of that dendritic growth zone close to the surface. And we see from all of this a correspondent change in the snow rate and an increase in the snow to liquid ratio, which means lower density snowfall. So the point of this is that with these instruments, we can observe this abrupt transition on the order of like minutes, right? This is like happening very fast, 10 to 20 minutes, this transition happens. And we see a corresponding fundamental change in the snowfall microphysics. So that's the power of this augmentation with these suites. So let's see my time. Coming back to here, I was just going to tell you, why should we trust? So I've told you, oh yeah, the PIP's this amazing instrument, and you can totally trust it. We actually did a whole study leveraging the Marquette data and the National Weather Service forecasting observations to convince ourselves we could trust this data. So I mentioned, I've shown you some particle size distributions, but I also mentioned we can get effective density and liquid water equivalent rate out of this, which is really hard to get from radars, right? Because of all these assumptions you have to make. So I'm not going to get too much into this figure, but we're able to empirically derive bulk snow density and bulk snow rate based on this model and relating inputs of particle diameter, what's on this lower axis here, and particle fall speed. And then through an empirical and theory-based relationship, we can get bulk snow density and bulk snow rate. So we have rain theory on one end, based on terminal velocity as a function of droplet size. And we have some snow observations on the other end that are bounding our conditions. So I know this is a lot to take in, but I just want to convince you that we did some experiments here to try to like see how well this model could produce snowfall rates with these inputs of diameter and fall speed. So we validated this using high and low density events in Marquette and independent observations from the NWS, as well as some mass retrievals from the Finnish Met Institute. So my colleague, Anna-Kaisa von Lerber, which you see down there, von Lerber snow rate, she has developed a mass retrieval using radar, radar observations from the PIP, observations from bucket gauges. Like she combines all of those and gets a mass retrieval, so liquid water equivalent. And so what we did is we took the high density events and the low density events, and this is log scale, just FYI. But the y-axis is the PIP snow rate. So what you can see there is we see very good agreement. So that gave us a lot of confidence. Okay, so we agree really well with Anna-Kaisa, who has this paper published in 2017, mass retrieval. That gave us a lot of confidence. Additionally, we looked at the NWS observations. So the National Weather Service forecasters take observations every 6 hours. And even though the temporal resolution is lower, that's good because we aggregate more statistics along that 6-hour period to compare. So again, here we have accumulation in liquid water equivalent millimeter from the snow stake from the NWS obs on the x-axis and the PIP on the y, again in log scale. And we see this excellent agreement. We looked at high density events, we looked at low density, and a couple of these green dots are those transition events like the one I just showed. The important thing about this is that the PIP does this at a high temporal resolution. It does this minutely, so you don't have to wait 6 hours to get agreement. And it's completely autonomous. Anna Kaisa von Lerber's method is excellent, but it requires like 3 or 4 different instruments. All right. So I just wanted to talk about some of the major, initiatives we did there from our JMC paper and our BAMS paper, and then this recent PIP one. But I wanted to talk about what we've done since then to like further build. We have this 10-year data set. We want to do some neat studies where we can get multi-season, starting to get into like, we can't really say climatology, but starting to like hedge on some longer timescale stuff. So we're building on the long-term observations and expanding throughout the Great Lakes region. I'll talk a little bit about our NOAA project. And then we've done some examinations of the impact of inland atmospheric rivers, which relates to atmospheric blocking for those who are interested. And then regime partition precipitation by inherent microphysical characteristics. So I'll just spend a couple minutes on these. And the only reason we can do this is because we have more than 10 years of data. All right, so a couple years ago, myself and Steve Nesbitt, we wrote a proposal to the Weather Program Office at NOAA to demonstrate what we did in Marquette, but let's take this across the Great Lakes and try to look and deploy similar instrumentation at 2 more sites. So we have a similar profiling radar and PIP particle instrument at Gaylord, Michigan, which is great because they have radio soundings and they have a double snow fence inter-comparison reference standard. And then at Buffalo, and this is the UI SCAMP, and it's hard to see here, but there's a profiling radar, there's a bucket gauge, there's met data, there's a different type of distrometer that uses lasers called a Parsifal, but still gives you particle size information. So we were able to do this for winters 21, 22, 22, 23, and we were doing it this year as a bonus year as well. This has involved a great team. This is like, there's like 2 things I love about this. This is a big team, but it's also, we're on the Great Lakes. So that's really fun. So it's led by me and Steve Nesbitt. We have a great team of people, including folks at Sigler that have been part of this. Steve has a grad student who's getting her master's, Mackenzie, who's finished up work on this. Jack Richter, who's a grad student in my group, has done stuff. He's mostly working on GPM work, but he's done some ancillary work to this. We have a great group at UW doing modeling. Abby Hudson here is doing modeling. John Lenters was at Michigan Tech, but is now at Michigan, and he's been providing the flux data. We have NOAA partners, Mark Cooley, David Wright, Jeff Wallstrecker, and then we've partnered with 4 NWS offices, which is great. Originally it was 3, but Greg Mann wanted to join, and we were like, yes, please. So we have this great group across the Great Lakes, so it makes for a nice visual for our team as well. One thing I want to say about this, one of the goals was this, is that we wanted to recommend, remember I said it's really hard to get next rad reflectivity Z to snow rate, what actually the liquid water equivalent. So one of our goals here was to say, hey, is there a different Z to S relation for deep snow versus shallow snow? And at Marquette, there is. Spoiler alert, at Gaylord, not so much, and we're trying to figure out why that is. We think the lakes, being surrounded by 4 lakes, is modifying a lot of things. But this is a bit of an older figure, but this is from Jack, and we see a very different deep snow relation. So it's hard to see the colors here, but the dots and the black line going through them is the empirical fit of the Z to S, which you can see compared to the shallow snow. Is much closer to that orange line, where the deep snow is much higher. So we have the PIP liquid water equivalent and the next rad reflectivity here. The main takeaway of this is that they don't have the same empirical fit. So we know fundamentally we have that idea where it's like you get a reflectivity, it can mean a lot of different things. So we're providing these to the NWS offices to help recommend different Z to S relations based on weather regime. Also, I wanted to feature some of Abby's work she's been doing. She's been doing this very cool WRF modeling of specific cases that hit Marquette, then Gaylord, and then Buffalo. So we have 3 cases that really interact with all 3 sites. And she has focused on looking at how well are the microphysics being captured here. And this is one of those transition events. So the reflectivity you see here is actually synthetic from the WRF model. But in these 2 highlighted regions, she's compared the particle size distributions from the modeling schemes, those are in those lines, versus what we see from the PIP, and those are in the circles. So you can see the time during the deep on the left there, those slopes look really different than the shallow on the right. Also, on the left, during deep, we have good agreement between the Thompson scheme and the PIP observations, but on the right, we see a bit of a difference between these assumptions. So we're digging into that. We're also looking at different microphysics schemes. This has been a really fun project. With my last couple minutes, I wanted to talk about two other highlighted projects that we did by virtue of having all this data. And one involves atmospheric rivers. I think everyone here is familiar, but I like to show this animation of kind of a classic atmospheric river coming from Hawaii to the east, to the west coast, like what's happening in California today. There's long, narrow regions of the atmosphere that transport statistically significant high amounts of water vapor meridionally. These, and I'm not going to talk about today, but my other projects looking at the high latitudes really focus on this because how that warm, moist air gets to those high latitudes is really key. It's not limited to coastlines. That's all you hear it talked about. But we actually see a big impact here in the Great Lakes region when we have atmospheric rivers. These are key takeaways from Marion Maitling led this paper. It's great. It's in JGR Atmospheres if anyone's interested. And some of you who are hydrologists might be really interested in this work. But we looked at wintertime precipitation, and we looked at these inland atmospheric rivers focused around Marquette, but atmospheric rivers are huge. They're hitting a lot of the community on their way up. And so in the top here, you're seeing a heat map of the counts of when we saw an atmospheric river. And on the bottom, you're seeing the actual water vapor transport. So those wind barbs and the concentration, the magnitude. What we found is during the winter, the deep synoptically forced cold season precipitation is associated with ARs almost 30% of the time. A lot of them are associated with an atmospheric river, per the definition we used, caveat there. So AR frequency during snowfall events and composite IVT magnitude during snowfall events. So we can see they're coming from the Gulf. You can see that from a composite sense, a lot of that moisture is coming up from the Gulf. It's hard to see these numbers, so I'll just summarize. The main takeaway is that precipitation rates are enhanced, statistically significantly enhanced, and rain is 4 times more likely to occur than snow if an AR is proximal. So we see this both from the MR reflectivity, we saw higher reflectivity, we saw PIP had higher precipitation rates, and the wintertime fraction of rain is 20% when you have an AR and 5% when you don't. So this is back to that rain on snow. This could have serious hydrological kind of impacts in the region. Finally, this is interesting because I just read an article about people looking at wintertime precip in the eastern US, but we found that these atmospheric rivers that hit the Great Lakes region are significantly correlated to the negative phase of the Pacific North American pattern and the Pacific decadal oscillation. And that's what you're seeing here are geopotential height anomalies. You're seeing a trough ridge. We see this anomalous ridging over the northeast in Conus in Canada. And this really is important because when we start thinking about subseasonal, seasonal, S to S, which NOAA and a lot of agencies are really thinking about these days, this is an important implication for wintertime precipitation because this has to do with the PNA and PDO are teleconnections, right? So they're on long time scales and it's related to atmospheric blocking. All right, the last thing I want to talk about with ARs, I've got about 5 more minutes. I promise that I'll let you guys all go. Coming back to this idea that we can characterize the microphysics, what are the microphysics during these AR events? And so I have a grad student, Jack Richter, he's prepping this paper for GMC, thinking about the impact of atmospheric rivers, not just at Marquette, but also in Finland and a couple other long-term sites, when you have a coincident atmospheric river versus not. So what we have here are 2 composites that are differenced. So on the left side, we have fall speed versus diameter, and on the right, we have effective density versus diameter. And when there's more red, that means it's more associated with an atmospheric river. And so what we see when you have atmospheric rivers and you have snowfall, we see higher fall speeds of the particles. We also see higher densities. These are, of course, coupled. But this is telling us that when we have atmospheric rivers, we're seeing denser particles that are falling faster in the atmosphere. So this tells us something about the mass of the particles. All right, these are just teasers. The last thing I'm going to talk about is we're not just limited to Marquette. In fact, we have identical suites that myself and others have helped facilitated in a ton of places in the Northern Hemisphere. So I collaborated with all these people, and I'm really excited about this work because this is something that I proposed in my NASA early career proposal, and I've been wanting to do forever, but it sounds kind of boring, but I wanted to get all the data together so that people could use it because it's really important. So what you're looking at here, it might be hard to see. On the left side, we have all the different locations. We have these coupled profiling radar and PIP observations because I've hopefully demonstrated that these really do enhance our understanding of snowfall and wintertime precip. So these are all the locations we have it. And then on the right, we see how long in the uptime. So you can see some of these have multi-year data sets. Some of them were a single season. Some of them were a couple seasons in a row, right? So we have observations from over 10 years throughout the Northern Hemisphere at 10 different study sites. And we could have added more, but we really wanted to just keep it strict that all the instrumentation was the same and all the software version was the same so that we could really be delivering the exact same products to stakeholders. And this is just a teaser, but this data set allows for all kinds of comparisons, macro and microphysical characteristics of precipitation from a variety of geographic and environmental regimes. And what I'm showing here, I'm not going to get into this, but it's just frequency plots of rain rate on the left and snow rate on the right at these different sites. Basically what this is showing is, hey, these different sites show different characteristics of heavy versus light precipitation. And even just starting there, that's a good piece of information to have. All right, I just wanted to tease some of that recent stuff we've been doing because it's really been facilitated by the Marquette site. All right, coming back, these are some of, I'm happy to like talk to anybody if you're interested in any of these papers. I covered a lot from these different papers. I just want to remind people, so we've been in operation since 2014 in Marquette. Since that time, we had the MRR, the profiling radar, and the PIP, of which I showed a bunch of data. We then added a Parseval 2, which is a laser disdrometer. So we have another piece of information about particles, and pluvios, which are those bucket gauges. We actually did a network for 3 years in the region. And we had 1 year of a LiDAR oscillometer data. So we're still digging into some of that and excited, especially about the LiDAR oscillometer, of what that's going to show. Lastly, this is what I showed, but it's just a piece because we have a lot of stuff going on. We are using observations from all these long-term sites. It's hard to see, but they're outlined in green. We have past and recent field campaigns in blue, and we have these future, current, and planned efforts, and I'm hopefully going to add a couple more stars there in a month. And so we have a lot of observations for those who are interested all over. And of course, we continue to use satellite observations. I didn't get to talk too much about the satellite studies we've been doing, but if you're interested, please let me know. Okay, and with that, I am happy to take questions. Thank you for your time. Exactly 50 minutes.
Thank you, Claire. Any questions from the room? David.
Thank you, Claire. I'm going back to your comment about the difference in sort of the Buffalo snow characteristics versus the Marquette. You're talking about, you know, sort of different lakes interacting there and things like that. How much do you think is, you know, residual layer on top of the surface layer coming from like Michigan influencing things? There's a lot that goes on, the microphysics, the state of Michigan there.
So what I was alluding to there is the, like, Buffalo gets this long lake access parallel, which is quite convective, and we don't really see that kind of lake effect. We see these cloud streets and these shorter parallel. There's some papers from the early 90s that kind of designate 5 different types of lake effect. It's more of that. But to your point, the NOAA project, we're hoping to do more of this, is seeing if there's any preconditioning. We're trying to dig into that. It's a really tough question. If there is any kind of preconditioning on stability, this could be stability, moistening, drying. But yeah, we would love to get towards some of that, but it's a really tough one to untangle. We're hoping the modeling can help with that. I think that's what we need to do.
And some of the modeling, preconditioning from Lake Michigan onto things, so we can.
Yeah, we should talk about that because like it's we have the additional like precip obs, so like how much does that dry the atmosphere as well, right? You have the preconditioning, but then if you snow it all out or rain it all out, then you've lost a bunch of moisture. So figuring out how that affects stability and how the downstream conditions is really interesting to us. That might be something, you know, the NOAA project's newer, but I'm going to try to get that data out to people as soon as possible. Yeah.
We have time for one more question. Is there a question from online? I think I have one question. I think I should into the microphone. So I was curious about what is your, I mean, I'm pretty convinced that snow microphysics and bulk density and all that has great impact on ice cover, but I'm curious your thought about ice pack on land, like basin, terrestrial ice, and like how that impact on snow water equivalent, the mass of snow, and that has a lot of consequences on to hydrological consequences, you know, has impact on runoff and all that. So I wanted to hear what you're thinking about that.
Yeah, and that gets to a good question because I talk to hydrologists a lot about this. You know, measuring snow once it's on the ground is a really different measurement than when it's like falling. One thing I think I can say to that is kind of what I alluded to, us looking at the wintertime phase of precipitation. So it's going to affect the snowpack. It's going to have a very short, it's on a very short time scale is going to have a big effect on the snowpack, right? Because it's going to basically drill holes into it. It's going to change the albedo effects. It's going to melt part of it away that might then wash away. And that's really hard to characterize from snowpack measurements, right? Like you might get, if you have a snow pillow or if you have something measuring the height of the snowpack, you might get a bit of that information, but you're not going to get information about how the albedo's changed or if it got porous, right? And of course, as the snow ages and the crystals round and stuff like that, they start to pack a little closer, but then you have a big warming event and they might melt and refreeze and then you get an ice crust. And it's super complicated. It would be nice. So UMBS now has one of these like laser altimeter, I think, style that just tells you like what the height of the snowpack is. And even just having that coupled with observations like these say, oh, we just saw a big event that had mixed phase snow turning into rain, that we could couple those together. But I think outside the SNOTEL network, which is really focused in the mountains, we don't have a lot of that information. But I do think it's really important to try to couple the information we have from the atmosphere to hydrology. Yeah. Always need more data.
Okay. I think we are on top of the hour. Thank you so much, Claire. You know, let's thank the speaker again.
Great. Thanks for coming in.